This is Module 7.4, Electrolyser Components. We'll now look more closely at the individual components of the electrolyzer with a focus on what a day-to-day operator needs to know. This section is only for information purposes, and we won't get into procedural details until another module. Here's an image of the front of the electrolyzer. By now you're familiar with the different components. Here's an image of the backside. The rectifier. The controls on the door are basic to the operation of the electrolyzer. We'll go through all the controls on the panel. Rectifier on indicator light. Rectifier start button. Rectifier stop button. These operate as you'd expect. Push the start button and the rectifier on light will illuminate. Push the stop button and the rectifier on light will turn off. The voltmeter shows the voltage applied to the cells. This is automatically set. The current meter shows the current flowing through the cells. To set the current, rotate the current adjust knob to the desired setting. Normally, we'd set it so the meter would indicate 150 to 170 amps. With the rectifier on and the current adjusted to 150 amps, the electrolyzer is said to be in production mode. The compressor is usually turned on and off by the gas holder limit switches, but for maintenance there may be a requirement to operate the compressor independent of the limit switches. Compressor on indicator light. Compressor start button. Compressor stop button. The door controls include an overload indicator light. This shows when an electrical overload occurs. The electrolyzer will shut off and turn on the overload indicator light. The electrolyzer won't start until the overload relay is reset, and that's done simply by pushing the rectifier start button. The emergency stop button. If something unexpected happens while at the electrolyzer, the operator can push the emergency stop button, which will shut down the electrolyzer immediately and turn on the alarm siren. In summary, to start the electrolyzer, push the rectifier start button, rotate the current adjust control until the current meter shows 150 to 170 amps. To shut the electrolyzer down, push the rectifier stop button. You could also shut the electrolyzer down by pushing the emergency stop button, but besides turning the rectifier off, it will also disconnect power to the electrolyzer and turn on a loud siren that will wake everyone up. So that should only be used when you need help right away. To open the rectifier cubicle, there are two screw knobs that are turned counterclockwise. You can see the inside contains a variety of electronic components, but only a few are of routine use by the operator. There is the low pressure switch we discussed when creating the model, and we'll talk about that more when we look at the scheduled maintenance checks you'll be doing. If we look straight in, we can see all the components you'll need to know about. There's the low pressure switch again. There are 4 electrical breaker switches that control the power to various circuits within the rectifier cubicle. There's an air filter that is checked and cleaned every month. Finally, there's a wind switch that's tested every month. To understand what the wind switch does, we need to step back a bit. Here's a view of the electrolyzer from the front and from the back. In the front view, you can sort of see the black pipe coming out of the top of the rectifier cubicle. That pipe extends outside the building. Inside the rectifier cubicle is a blower fan. It sucks outside air through the black pipe into the cubicle. The air circulates throughout the cubicle, ventilating it, and then the air is exhausted into the room. Through those ventilation holes you can see in the back image. By bringing in outside air, the rectifier cubicle is slightly pressurized, and it ensures that if there were ever a hydrogen leak, that the hydrogen gas wouldn't be able to enter the rectifier. If something happens to the airflow, if the inlet pipe is obstructed by snow for example, or if the fan motor fails, or even if the rectifier door is opened, then the sail of the wind switch will drop down, tripping the switch and turning the electrolyzer off. The wind switch will reset itself after the airflow is restored and the cubicle is pressurized again. However, after the wind switch resets, a time delay relay prevents the rectifier from being turned on for 60 seconds. just to make sure fresh purging air has flushed all the room air out of the rectifier, and that's just in case there was some hydrogen in the room while the purging airflow was off. In high winds from certain directions, it's common for the wind turbulence to cause a big enough pressure change outside the building that the airflow into the rectifier is affected. When this happens, the wind switch will trip, turning off the electrolyzer. In extended periods of high winds, that wind effect might prevent the electrolyzer from running for a number of days. In production mode, the current setting should be about 150 amps to 170 amps. Once the storage tank is filled to capacity, the high pressure switch will activate and turn the electrolyzer to idle mode with a current of about 30 amps and also remove power from the compressor. In idle mode, the current adjust knob doesn't do anything, and even pushing the compressor start button won't do anything. The electrolyzer stays in idle mode until the pressure in the storage tank drops and the high pressure switch resets. This low current level in idle mode means the electrolyzer will still produce a small amount of hydrogen gas, and it will fill up the gas holder to its highest level, and the excess gas will just vent outside the building. Idle mode is a protective measure to ensure everything in the electrolyzer remains pressurized so air can't get inside any component. When you learn about the monthly preventive maintenance, we'll go into more detail about cleaning the air filter and testing the low pressure switch. The cells. Here's a front view of the cells. You can see the sight glasses, the clear plastic tubes that allow you to see the level of electrolyte in the cells and allow you to know when the cells need more water. Every day you'll have to add water to the cells to compensate for the water that's been converted to hydrogen and oxygen. There is a water reservoir that the operators keep filled, and when the cells need water, a small valve on top of each cell is opened until the cell is filled to the right level. Here's another view of the cells. You can see the lines on the front showing the upper and lower limits for the electrolyte. Normally, you fill the cells to the upper line. Here's a closer view of the top of the cells. You can see the plastic hoses for adding water to each of the cells. Each cell has a red-handled valve for adding water. The copper bus bars conduct the electrical current from the rectifier into each cell. On the back side of each cell, there's a sampling port with a valve. Each week, you'll be conducting a routine sampling of the hydrogen gas produced by each cell. Below is an image of the handheld Firite sampler used for measuring hydrogen purity. You can see the clear plastic header tubes. The oxygen and hydrogen leave the cells through these tubes. Beside the cells, you can see the plastic tube taking the hydrogen to the water seal. The water seal. The water seal isn't very spectacular, it just looks like a metal can. Both the hydrogen and oxygen go through the water seal, and the water seal acts to equalize pressures in the cells and also prevents the two gases from recombining should the pressure in the cells ever be less than the pressure in the gas holder. From the front view, you can see the overflow pipe. Every day the water seal is checked to ensure it's filled with water to the proper level. On the front panel, there are controls and gauges associated with the water seal. Every day, the gas purity of the electrolyzer is checked. A sampling hose is connected to the hydrogen sampling port, and the hydrogen sampling valve is opened. Once the gas sample is taken, the hydrogen sampling valve is closed and the sample is tested. We'll have more detail about the sampling process later. Also on the front panel are the inlet and outlet manometers. The manometers are U-shaped glass tubes filled with fluid. In the first figure, there's no gas pressure applied to the manometer, and the fluid level is equal on both sides. The gauge reading is 0 inches. In the second image, gas pressure is applied to the manometer. It pushes the column of fluid down. The pressure reading is given as the total difference in the height of the two water columns. For example, the manometer on the right reads as 3.0 plus 3.0 equals 6 inches. For the gas to get to the gas holder, the pressure in the cells has to be higher than the pressure in the gas holder. The standard requirement is to ensure the pressure difference is at least 1 inch. In the illustration, you can see that the inlet manometer on the left is reading 3.5 plus 3.5 equals 7.0 inches. The outlet manometer on the right is reading 3.0 plus 3.0 equals 6.0 inches. 7.0 minus 6.0 equals 1.0, so the pressure difference is good. If the manometers are set up properly with the proper amount of fluid inside each one, the inlet manometer on the left should always have its left-hand column lower than the left-hand column on the outlet manometer. So the inlet manometer shows the pressure of the gas coming from the cells. The outlet manometer normally shows the pressure of the gas holder. The gas holder vent valve is normally directed to gas holder, but during maintenance and testing it's routine to turn it to vent, so the hydrogen gas produced just goes outdoors until the testing is completed. When this valve is directed to vent, the outlet manometer shows 0. The gas holder. Here's an image of the gas holder with the bell at its highest. The gas holder relies on water in the lower chamber to allow it to float. One of the daily checks is to ensure the gas holder is full of water to the proper level. Here's a closer image of the gas holder. In the image, you can just barely make out that there's a metal cable hanging from the gas holder. It shows up as a black line. This cable hangs down into a vertical pipe. At the end of the cable is a metal weight. When the gas holder gets to the top, that metal weight pushes against a lever that activates a switch. When the compressor has drained the gas from the gas holder is at the bottom of its range, and the metal weight pushes another lever that activates another switch to stop the compressor. In the model discussion, we described the two limit switches. The upper limit switch turns the compressor on when activated by the metal weight hanging from the gas holder. The lower limit switch turns the compressor off when activated by the metal weight. But what if something happens and one of these limit switches fails to work? If the first upper limit switch fails to work, the bell will continue to rise and activate the upper limit switch. This turns off an indicator light in the office to notify staff. The gas holder bell will be riding high and the internal gas holder vent line will be exposed, enabling the hydrogen gas to be vented outdoors, so there is no hazard. Similarly, if the first lower limit switch fails to activate, the bell will continue to drop and will activate a lower limit switch that will immediately turn off the electrolyzer. The operation of these 4 limit switches is tested every week. What if the lower limit switch fails to work? Well, if the lower limit switch fails to turn off the compressor will keep running and try to suck out every bit of gas from the gas holder. This will greatly reduce the pressure in the gas holder, and that activates the low pressure switch located in the rectifier cubicle. This is such a serious problem that not only will the low pressure switch turn off the electrolyzer, it also activates the alarm siren. The low pressure switch is tested every month as part of the regular maintenance procedures. In this view of the rear of the electrolyzer, you can see the gas holder vent valve used to empty the gas holder. This is usually only used by maintenance staff. The compressor. A metal grid is in front of the compressor to ensure nothing gets caught in the rotating pulley. If we remove the protective grid, you can see the compressor better. The electric motor underneath turns the drive pulley. The drive pulley turns the main pulley. The main pulley drives the compressor. The coil allows the gas to cool after compression. In the back is the dipstick. Every week, the operator unscrews the dipstick and checks the level of the lubricating oil. Here's a view of the compressor from the front. The compressor itself is above the electric motor that turns the pulley. After the compressor pressurizes the hydrogen, the gas goes through a cooling coil and any moisture is collected in the Ballston filter. Normal daily maintenance is to drain accumulated moisture from the Ballston filter by first opening, then closing the drain valve. On the front panel, there are controls for the compressor. The compressor pressure gauge shows the outlet pressure of the compressor. The high pressure switch is located immediately behind the panel and is activated when the storage tank is full. The compressor inlet valve, when open, allows gas from the gas holder to enter the compressor. It's open during normal operation and only closed for maintenance and testing. When it's closed, no gas can get into the compressor and an associated electrical switch interrupts power to the compressor, so the compressor will not run. The pressure differential switch is a safety feature that will turn off the electrolyzer if there's a sudden drop in pressure in the high pressure line. It would be triggered if there should ever be a leak, for example, but it's also routinely tripped during normal balloon inflation, so it's tested every day. The PDS pressure gauge shows the pressure at the switch. The PDS switch itself is located immediately behind the panel. There's an audible click when the PDS switch trips. If the electrolyzer is running at the time, it will be turned off and can't be restarted until the switch is reset. The PDS switch is reset by first opening then closing the PDS reset valve. This equalizes the pressure on both sides of the switch. The tank filling valve, when open, allows the compressed gas to go to the storage tank. The balloon filling valve connects to the inflation valve, which is used to control the gas flow when filling a balloon. The inflation valve is mounted on the far wall and is used to control the process of filling the balloon. The technician can stand at the inflation valve and through the door watch the balloon being inflated in the next room. The storage tank. The storage tank typically holds enough gas for about 8 balloons. The pressure relief valve is an emergency device that will vent the gas if the pressure gets too high. The pressure gauge shows the tank pressure. The condensate blowdown is a valve used to drain any moisture that has accumulated in the bottom of the storage tank. Here's a closer view of the pressure gauge. It's reading 96 psi. Note that there are 2 valves, one on either side of the gauge. These valves can be used to isolate the pressure gauge if necessary. For example, if the gauge needed to be replaced. The valves are also used for testing. For example, by closing the valve closest to the tank, you can run the compressor and quickly see how fast the pressure in the lines increases and at what pressure the high pressure switch will activate. Here's a closer look at the condensate blowdown at the bottom of the storage tank. This piping leads from the bottom of the tank to the vent leading outdoors. Every day, the technician pushes the relief valve to blow a small amount of hydrogen out the vent. Any moisture at the bottom of the tank will be forced out as well and will collect at the end of the pipe. Then the technician removes the cap and drains the water away. Here's a close-up view of the pressure relief valves at the top of the tank. If the pressure in the tank exceeds 150 psi, the pressure relief valve is activated and vents the gas out through the pipe leading outside. On Sable Island there are actually 3 pressure relief valves together with a toggle valve that allows the relief valves to be removed for testing. The wall vent. In the model, we described how the hydrogen gas could be vented outdoors. 1. By setting the gas holder vent valve to vent, and 2. By the internal gas holder vent line that is exposed when the gas holder is riding at the top of its travel. For example, if the storage tank is full. Here's the entrance to the electrolyzer room and the wall vent above the door. This is visually inspected every day to ensure it's clear of obstructions. This is what the vent looks like inside the room. The vent housing has a built-in heater to melt snow and ice to ensure the vent doesn't get plugged up. There's a temperature gauge, Fahrenheit degrees, mounted on the housing. If the indicated temperature drops, it would show that either the vent was plugged with snow or the heater had failed. The temperature of the vent heater is checked every day. The Pyrite sampler. To ensure the electrolyzer is producing pure hydrogen, we regularly test it to determine if there's any oxygen in it. The tester is called a Pyrite sampler and contains a dark blue fluid. When we push the top plunger down and introduce a gas sample, the fluid absorbs oxygen and increases in volume. That increase is measured on the scale on the right-hand side. The hydrogen gas from the electrolyzer normally has 0.0% oxygen. The room air has 21% oxygen, and testing the room air is the standard test of the accuracy of the Pyrite sampler. Gas is added to the Pyrite sampler with the aspirator bulb assembly. The end of the hose plugs into the sampling port. The woolen filter material is periodically moistened with water, just enough that it feels moist to the fingers. If it's allowed to dry out, it will make the Pyrite sampler read slightly low. If it's dripping with water, it will make the Pyrite sampler read slightly high. The aspirator bulb is squeezed repeatedly to suck in a gas sample and blow it out the tip. The demineralizer. The electrolyzer uses demineralized water in the cells, and the water is obtained from a water filter in the operations building. Every day, the water reservoir in the electrolyzer is filled from the plastic water jug, and when the water jug is empty, it's taken back to the operations building and refilled. This completes the description of electrolyzer components.